In this video, we will practice 5 of the 7 theorems that you need to know for AP Calculus. In previous videos, we talked about the first fundamental theorem of calculus, which taught us that the end value is equal to the initial value plus the net change in value, which is given by the integral of the rate. And then we learned about the second fundamental theorem of calculus, which taught us how to take the derivative of an integral defined function, either in the common case where you just plug in the x and you get f of x, or in the general case where you have to do something that sort of reminds you of the chain rule. In addition to the first and second fundamental theorem of calculus, there are 5 other theorems that you need to know. The first is the intermediate value theorem, or IVT, which says if f is continuous on the closed interval from a to b, and f at a is less than k, which is less than f at b, there exists some c on ab such that f at c is equal to k. In other words, imagine that f at a is here and f at b is here. Now imagine some value k that is between f at a and f at b. If f is continuous, then we are guaranteed to hit that value k at some point. In other words, we are guaranteed that there is some value c such that f at c is equal to k. And that's the intermediate value theorem. Next, we have the extreme value theorem, or EVT. This is pretty self-explanatory. If f is continuous on a closed interval from a to b, then f has both a minimum and a maximum on a to b. And this is an absolute minimum and an absolute maximum. Next, we have Rolle's theorem. For this theorem, f has to be continuous on the closed interval from a to b and differentiable on the open interval from a to b. And it says if f at a is equal to f at b, then there is a value c in ab such that f prime at c is equal to 0. In other words, imagine that f at a is here, and then f at b has the same exact value. If function f is continuous and differentiable, so there can't be any corners or cusps or discontinuities, then we are guaranteed that there is some point between a and b where f has a horizontal tangent line. We are guaranteed that there is some point c at which f prime at c is equal to 0. Rolle's theorem is really just a special case of the mean value theorem, MVT, which says that if f is continuous over the closed interval from a to b and differentiable over the open interval from a to b, then there exists some c in ab such that f prime at c is equal to f at b minus f at a divided by b minus a. So what does this really mean? The mean value theorem is just saying that there is some point c where the slope of the tangent line is equal to the slope of the secant line. Let's say f at a is here and f at b is here. This purple segment is the secant line. If function f is continuous and differentiable, then we are guaranteed that there is some point c where the slope of the tangent line is equal to the slope of the secant line. Of course, the slope of a tangent line is f prime, and the slope of a secant line is the old school slope y minus y over x minus x. Finally, we have the mean value theorem for integrals, which says that if f is continuous on the closed interval from a to b, then there exists a number c in ab such that f at c is equal to 1 over b minus a times the integral from a to b of f of x dx. Hopefully you recognize this formula as the average value formula. So in other words, the mean value theorem for integrals says that there's always going to be a number c such that f at c is equal to the average value of f of x. So you see that we have two different mean value theorems. We have one for derivatives and now one for integrals. But if you ever just see mean value theorem, it automatically means the one for derivatives. If they want to refer to the mean value theorem for integrals, they have to specifically say for integrals. I want to highlight one difference between the two. Notice that the mean value theorem for integrals is about the value of the function at c, just plain old f at c, whereas the mean value theorem for derivatives is about f prime at c, the slope of the tangent line. Let f be a function that is continuous and differentiable everywhere. Determine whether each statement is definitely true, justify using a theorem, or possibly false, give a counterexample. Assume that b is greater than a for all problems. Problem number 1. F takes on its absolute maximum value at exactly one x-coordinate on the closed interval from a to b. The extreme value theorem guarantees that function f does have an absolute maximum on the closed interval from a to b. However, it does not say that there is exactly one x-coordinate. So this is possibly false because f of x could equal its max at more than one x value. Here's a counterexample. F of x could hit its absolute max at c and d. Problem number 2. If f at a is less than k, which is less than f at b, then there is some c in the interval from a to b so that f at c is equal to k. This one will definitely be true because it is just a restatement of the intermediate value theorem. So this is definitely true by the intermediate value theorem. We are given that f of x is continuous. Since f at a is less than k, which is less than f at b, there is a c on ab where f at c is equal to k. So basically, I've just rewritten the intermediate value theorem. Number 3, if f at a equals f at b, then there is some c in the interval from a to b so that f prime at c is equal to 0. Problem number 3 is simply Rolle's theorem. If f is continuous and differentiable, then if f at a is equal to f at b, then there is a c on ab such that f prime at c is equal to 0. So I'm going to say this is definitely true by Rolle's theorem, and then I'm just going to state Rolle's theorem. F of x is continuous and differentiable. Since f at a is equal to f at b, there is a c where f prime at c is equal to 0. Notice that for each one of these theorems, there is an initial set of conditions that must be met before you can reach the conclusion. In the case of Rolle's theorem, f has to be continuous and differentiable, and f at a must equal f at b. Then you can conclude there's a c such that f prime at c is equal to 0. Before you use one of these theorems, you always have to state that the initial conditions have been met. So notice how I always say that f of x is continuous and differentiable, and then I'll say f at a is equal to f at b. Then I can say there is a c where f prime at c is equal to 0. Look back at problem number 2. First I said f of x is continuous. And then I could say since f at a is less than k, which is less than f at b. These are the initial conditions. Let's see if problem number 4 reminds us of one of our 5 theorems. There is some c in the interval from a to b so that f prime at c is equal to f at b minus f at a divided by b minus a. That was just the mean value theorem, the one for derivatives. All that is required is that f is continuous and differentiable. If that's the case, there is a c such that the slope of the tangent line at c is equal to the slope of the secant line. Number 4 is definitely true by the mean value theorem. We are given that f of x is continuous and differentiable. So there is a c on the interval from a to b where f prime at c is equal to f at b minus f at a divided by b minus a. That's just the mean value theorem. Number 5. There is some c in the closed interval from a to b so that f at c is equal to the integral from a to b of f of x dx. There's only one of our 5 theorems that involves an integral. Let's take a look. The mean value theorem for integrals says that if f is continuous on the closed interval from a to b, then there is a number c where f at c is equal to 1 over b minus a times the integral from a to b of f of x dx. This is the average value formula. How does this compare with problem number 5? Well, I see f at c and I see the integral from a to b of f of x dx, but there's something missing. This is supposed to be 1 over b minus a. It's the integral divided by the interval, and we're missing that division part. So there is no theorem that guarantees this to be true. So this is possibly false. All I need is to come up with a counterexample for which this is a false statement. Let f of x equal 2 on the closed interval from 0 to 4, as shown right here. The integral of f of x from 0 to 4 will be the area under the curve between 0 and 4, and the area of this rectangle is 8. But f at c does not equal 8 for any c on the closed interval from 0 to 4, which makes sense because f of x is always equal to 2. It's never going to be 8. Number 6. If f at a is less than 0 and f at b is greater than 0, then f has at least one 0 on the closed interval from a to b. Stop me when this sounds familiar. Let's say f at a is here and f at b is here. If the value of 0 is between f at a and f at b, then if f is continuous, we are guaranteed that f will hit 0 at some point between a and b. Hopefully you are recognizing this as an example of the intermediate value theorem. If f is continuous on the closed interval from a to b, and if f at a is less than k, which is less than f at b, there is a c where f at c is equal to k. Number 6 is definitely true by the intermediate value theorem. We are given that f of x is continuous. So, since f at a is less than 0, which is less than f at b, there is a c on the closed interval from a to b where f at c is equal to 0. Number 7. F has an absolute maximum value somewhere on the interval from negative infinity to positive infinity. This sounds a little bit like the extreme value theorem, but not so fast. The extreme value theorem guarantees the existence of both an absolute minimum and an absolute maximum on a closed interval from a to b, not an open interval, and definitely not negative infinity to positive infinity. So number 7 is possibly false. For a counterexample, let f of x equal x on the interval from negative infinity to positive infinity. This function clearly has no absolute maximum because it just keeps going up and up forever. For these last 5 problems, change the underlined part of each false statement to make it true. Explain why the change was necessary and how it made the statement true. Number 8. Here comes a false statement. The extreme value theorem guarantees that h of x, which equals x cubed minus 4x plus 2, has an absolute maximum somewhere in the open interval from 0 to 3. This is false because the extreme value theorem requires a closed interval from a to b. Let's change the open interval from 0 to 3 to the closed interval from 0 to 3. That way, the extreme value theorem will apply. Now the statement is true. Number 9. Here is the false statement. Rolle's theorem requires that j of x, which equals x squared minus 4, has a horizontal tangent line somewhere on the closed interval from 1 to 2. Rolle's theorem requires that j at a equals j at b for the closed interval from a to b. However, in this example, we have the closed interval from 1 to 2. J at 1 is negative 3, while j at 2 is 0. So we can see that j at 1 does not equal j at 2, as required by Rolle's theorem. To fix the problem that j at 1 does not equal j at 2, we can replace the 1 with a negative 2. Since j at negative 2 does equal j at positive 2, Rolle's theorem will apply. Putting in the negative 2 makes this a true statement. Notice that if we plug negative 2 in right here, we have a positive 4 minus 4, which is 0. And if we put a positive 2 right here, we also get 0. So j at negative 2 equals j at 2, and Rolle's theorem applies. Number 10, here is the false statement. The intermediate value theorem guarantees that g of x, which equals x to the 4th power plus 5x plus 4, must have a 0 somewhere in the closed interval from 1 to 3. The problem is that the intermediate value theorem does not apply because 0 is not between g at 1 and g at 3. If you plug in 1 for all of the x's, you get 10. If you plug in 3 for all of the x's, you get 96. So the intermediate value theorem guarantees that a continuous function g will hit every y value between 10 and 96. However, if you want to guarantee the existence of a 0, we need to set it up so that g at 1 is less than 0 and g at 3 is greater than 0. Or it would also work if g at 1 was greater than 0, but then g at 3 was less than 0. 0 just needs to be between g at 1 and g at 3. Let's replace the 4 with a negative 10. Now g at 1 is negative 4. And g at 3 is equal to 86. So 0 is now between g at 1 and g at 3. This means that the intermediate value theorem applies, and g of x is guaranteed to hit 0 somewhere on the interval from 1 to 3. In other words, now g at 1 is less than 0, which is less than g at 3. So there is a c where g at c equals 0. Number 11. Here is the false statement. Given the function k of x, which equals x to the 3rd power minus 5, the mean value theorem for derivatives guarantees that there is some c on the closed interval from negative 1 to 7, where k prime at c is equal to 0. The mean value theorem for derivatives says that there is a c where f prime at c equals f at b minus f at a divided by b minus a. In other words, the slope of the secant from a to b. If you substitute negative 1 for x, you get negative 6. If you substitute 7 in for x, you get 338. The mean value theorem says there is a c where k prime at c equals k at b minus k at a divided by b minus a. But in this case, that gives us 338 minus negative 6 divided by 7 minus negative 1. But that turns out to be 43, not 0. In other words, the mean value theorem says there is a c on the interval from negative 1 to 7 where f prime at c is equal to k at 7 minus k at negative 1 divided by 7 minus negative 1. This equals 43, so replace 0 with 43. Last one. Here comes the false statement. Given the function k of x, which equals x to the third power minus 5, the mean value theorem for integrals guarantees that there is some c on the closed interval from 0 to 4, where k at c is equal to 44. The mean value theorem for integrals says that there is a c where f at c is equal to 1 over b minus a times the integral from a to b of f at x dx. I think of this as the integral divided by the interval. That is also known as the average value formula. So let's calculate the average value on the interval from 0 to 4 of this function k of x. So we will do the integral from 0 to 4 of k of x, which is x to the third power minus 5, and we will divide by the interval 4 minus 0. I'm betting that this does not turn out to be 44. So whatever we get, we will replace the 44 with this value. I forgot the dx. So when we integrate, I will increase the exponent by 1. So I will get x to the fourth power, and then I will divide by the new power. So I will have 1/4. And then moving on to the negative 5, this will become negative 5x. We must integrate from 0 to 4. So I'm going to put on my limits of integration. All right, all of this is divided by 4 because 4 minus 0. Now I am going to find the value at 4 and subtract the value at 0. So here's the value at 4 minus the value at 0. This comes out to be 64 minus 20 divided by 4, which equals 44 over 4, which is 11. In other words, the mean value theorem for integrals says there is a c on the closed interval from 0 to 4, where k of c equals 1/4 times the integral from 0 to 4 of k of x dx. But this integral equals 11. So replace the 44 with 11.